concept of what is an enantiotopic and distereotopic, there is a handout on your Elm site that will cover for you how to discern if something's an enantiotopic or distereotopic. There's a bunch of people in my office yesterday asking about what an enantiotopic and distereotopic were. They didn't know, so I put something under the handouts section folder on our Elm site that will help you make that discernment. And there's also 3 problems to try at the bottom, and on the second page there's answers. So there should be enough there to do that. Now, in the meantime, today we're going to start with the C3H6O, and C3H6O, in essence, does have an example of distereotypicity, okay? If everyone flips over to the back, okay, that on the bottom is the answer to the structure. So that is the answer that says to you what the structure is, and you should be able to assign every one of those protons in the spectrum. I did that for you, but I'm just saying you should have been able to do that, to say this one's A, this one's B, this one's C, this one's D, this one's E, I think is what it is, right? Okay. Sometimes I put A for HA on the alcohol. Remind yourself that the alcohol falls everywhere. Oftentimes I begin to label that Z because it doesn't always fall the furthest upfield, and it doesn't always fall this, so I usually just classify it as Z. So if you see that at any point in time, you know. So let's start here by trying to understand how these assignments were made. I did the splitting tree for you, and if you haven't seen a splitting tree before, this is how we actually can work out the multiplicity, so it's actually a nice way to do it. There is a section in your Loudon textbook that does it with you and for you and shows you how to do it. You can look for that in the NMR spectroscopy chapter. It's literally listed as complex splitting, which in essence are what distereotopic protons are. So I don't know if I'm going to try not to do the same one, but we can see. So I think I did this one here, right? I did HD, which is that one? Yeah. So I guess I'll do HC here today, so that we can sort of be aware of how this is. Now to start with, I've circled the 2 distereotopic groups. So let's be very quick and clear about why those 2 groups are distereotopic. The fact that they're distereotopic means that they are different, unique chemical shifts. They're unique environments. They have different chemical shifts, which is why you see 3,1H integrations in that alkene section 4 to 6, because each one of these protons are unique environments. Now, C and D is a little bit harder because it seems like they share the same environment, but they don't really, because HD is always locked, right? Locked trans to that CH2OH, and HC is always locked cis, right, on the same side as that CH2OH. So in essence, considering the environment, right, it's a 3-dimensional environment, they do have different environments. That, C and D do have different electronic environments, we would say. But if I were to classify them very quickly, the handout will say to you, take the 2 groups in question and make them a heavier isotope. Give one priority, which in essence you can do by making them a heavier isotope. If you remember your Conning-Gold pre-log rules, they state that you take priority based on atomic number. But if all else fails, they have the same atomic number, you can use atomic mass. So what we do, first and foremost, is we create 2 imaginary molecules where I swap out each one of the groups separately for a heavier isotope. So I'm going to do that. I'll swap out HD first, okay, leaving HC there as an H, and this is the imaginary molecule I come up with, okay? This imaginary molecule, if I were to classify it as E or Z in terms of the alkene, right? This is the high priority group on the left sp2 carbon. This is the high priority group on the right sp2 carbon. They are trans to one another or on opposite sides, so this is an E alkene, right? So this is my first imaginary molecule where I've replaced a hydrogen with a heavier isotope. Remember, heavy hydrogen is deuterium, right? 2H, adding a neutron, is deuterium. We name it deuterium as opposed to 2H. I don't know how that started. Now I'm going to make my second imaginary molecule here. here's my second imaginary molecule, and I see that in this case, I've created a Z alkene, okay? The handout will say, make two imaginary molecules where you swap out the groups that you're considering the relationship between for the heavier isotope, exchanging one out in the first imaginary molecule and the alternate out in the other imaginary molecule. Assign the configurations to any stereocenters. The stereocenters we have here are the alkene center, one is E and one is Z. The last step is to determine the relationship between these isomers, and these isomers are actually distereomers, okay? EZ alkenes are distereomeric, where one site, one sp2 center has the same configuration, right? And the other has the alternate configuration. They're distereomeric, and therefore the two groups in questions are distereotopic. Any distereotopic protons, again, have unique chemical shifts, and that's where this whole conversation about distereotopicity and enantiotopic came in, okay? I remind you that if you distinguish the relationship between the two groups to be enantiomeric, therefore the groups are enantiotopic, that does not play out in the NMR at all. Those two protons will be in the same environment, or two groups will be in the same environment, okay? So I'm going to ask that you accept that these two protons here, HD and HC, are distereomeric. They have unique chemical shifts. You can see that in the NMR. And I'd ask that you go to the handout, practice, make sure you can do something like that. And if you still have questions, by all means, come into the office or ask him. We are happy to help you, okay? But for today, I want to go on to the multiplicity as we were talking about at the end of last class, okay? So we're going to start with the multiplicities, and I'm actually starting with a harder example, right? Actually, this is the example I'm going to get to, but maybe we should start with an easier example and do a splitting tree, okay? We had, I can't remember if it was methylethanoate or acetate, or was it ethyl formate? What did we have?
Ethyl acetate.
Ethyl acetate, thank you. Okay, all right, that's helpful. So this is the molecule we were doing last time. So today, I'm going to do the splitting tree for this guy out here, okay? And just for sake of keeping away from D, A, C, E, whatever, I'm going to call this J. We'll just call it J for today, okay? So this is HJ. I'm going to do the splitting tree for HJ. Now you know already, you have the answer, you saw it last class, you know it's simple splitting. Anytime my neighboring carbons are sp3 nature, it's simple splitting, okay? Which means I can follow simply the n+1 rule. So I already know that HJ has two other HJs that are like it, right? But there are two protons in the neighboring environment, right? Or the neighboring carbon, pardon. And these two protons account for N, capital N. If I plug that in the n+1 rule, 2 plus 1 is 3, I know I get a triplet, okay? Now, what we actually track as sort of the physical property of what this coupling constant means is a J value. I don't know if you've ever heard of that. That's going to be confusing, right? Okay, so we're going to change this. This is going to be K. Okay, so we actually call a J value or a coupling constant. And a coupling constant is in essence how much influence the neighboring protons have. You don't all have to influence that proton of interest the same. That doesn't necessarily occur. It does occur if all of the protons on neighboring carbons are all from sp3 centers. That then is true. They're all the same because they're all on neighboring sp3 centers. And there's free rotation, right? So that means, right, that it's all going to be averaged out. They're all the same. That's not true when we get to these centers here that have sort of locked in stereochemistries. But suffice it to say that any proton on a neighboring sp3 carbon has a coupling constant that has a mathematical value, and its value is generally between 6 and 8 hertz, so we'll go with 7 hertz, okay, just for, averaging sake. Always, 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 it's 7 hertz, okay? Now, how do you get that split of a triplet, okay? That's what I want to explain to you, because that helps you understand these crazy coupling trees, okay? This is how I get the split for HK as a triplet. I say, okay, HK, if it didn't have any neighboring protons, would be a singlet, right? and you can give it a height. I don't know, give it a value. Do like 120. Okay, this is just a measure of how much area there is under the peak. I'm just tracking it numerically. Okay, so that would be HK if there were no neighboring protons. Now every neighboring proton, every single one, will split this 50-50 into an upfield and a downfield component. 50-50 into an upfield and downfield component. So here I go. 50% of this, right, into an upfield component and a downfield component. Truthfully, this was upfield, right? Upfield component and a downfield component. We do the NMR axis, right, where this is upfield towards 0, and that's downfield. And the split between here could be measured in this value hertz, right? And it would measure as 7 hertz, okay? That's where the mathematical value comes in. It's a measure of that split. If you ever get out a ruler, right, you can measure it in millimeters, and you can take that, if you know what spectrometer it was collected on, you can get a hertz value for that. But that distance, if you ever notice, is always the same in those splits. It's crazy, but it's true. So this split is a 7 hertz split, and I have 60 here, because I've split it half, right? And if the area is 120, now it's 60. Is everyone with me? Okay, so this is one proton's influence. Every proton does the same thing, but they do them one after the other. They do them in continuum, okay? So I've only taken one of them into account. I have to do every neighboring proton, so the second one I do is going to take each one of these and split it 50-50, okay? So when it splits 50-50 here, I'm going to go here, and then this guy's going to come here and here, right? Where this is, I'm not very good spatially, obviously, you can see, because this is not the same distance. But generally, the splits are going to be 70 hertz, right? Where the area 30 comes when I split this peak on the left, downfield, 30 comes here. 30 is totally going to come to the same exact spot here. I'm just showing them right next to each other, but this is the same exact spot. And 30 is going to come here. So in the end, my area of the peak is 1 to 2 to 1, or a triplet. I'm going to read this out. It's going to be 1 to 2 to 1, with a 7 hertz split along each of these. Okay? Does everyone see how this triplet came about? You're so used to using the n+1, but this is it. This is the splitting tree. Yeah?
What is this 120 number? What are all the numbers?
So the numbers represent just the area, right? The integration under the curve. So it gives me a sense of area. I want to say specifically that 50% of the signal goes this way and 50% of the area moves this way when it splits, is what I'm trying to say. So the numbers represent the area under each one of those peaks. Yeah? Now that's a very theoretical question. It splits because the neighboring proton, whether or not the neighboring proton nuclei is with the field or against the field, is going to influence where this falls in its chemical shift. That's a crazy answer, right? NMR theory is absolutely crazy. There is an answer to it. I think probably best to know that it just does split it equal. But I'm happy to go over the theory with anyone who's interested. I'm happy to go into it more. Yeah.
And the very top one doesn't necessarily represent just one proton. I mean, it could be in just one environment. So it could be,
Yeah. Right,
okay.
exactly. Yes. Whoever.
If you, we knew this was a triplet, but if you didn't know it was a triplet, how did you know when to stop splitting?
I stopped splitting when I stopped having neighboring protons.
Okay.
So there we go, I'm done. So look, it is a triplet. We knew that going in, so yeah. Uh-huh.
I'm sorry, why did you cross off, which?
So this is to say, this here was the influence of that first one, right here. And this is the influence of the second one, so now I can cross that off. I just hadn't gotten to that. And now I'm done. I have no more protons on the neighboring carbons. I'm done. This is the end of my splitting tree, and I read it out as a 1 to 2 to 1 split, which is a triplet. Yes?
So why is the center peak larger than the other two?
Because as I move 50% of the area of this peak here and 50% here, they actually coalesce together, and that's why. Okay, I know you have more questions, and I want to answer them, but let's try an advanced splitting tree. I know that seems crazy. No, don't go there, because I want to ask my simple question. But an advanced splitting tree is actually hopefully going to sell this concept of the splitting tree and the importance of it a little bit more. So we're going to do HD is done for you on the back, okay? So I don't want to do HD because you might be able to use that to review. So I'm going to do HC. So you have a second one in your notes. Okay? So you don't know these numbers. You don't know these J values. They have to be told to you. So you can see on the back that there are these numbers, right? They're written out for you. You never ever have to know the numbers. Okay? So, but the numbers that are involved, that C is involved in, should be something like this. I should have an HCE split, right? That's about 15 hertz. I should have a CD and also a BC. All of those are going to be equal to one another, and it's going to be 2 hertz. So if you were to look on the back of your hand, on the back of the spectrum, you should be able to pull out all the J values that have C involved, and this would be it. Okay? You should see something that says CE or EC, it doesn't matter, it involves C, and that's going to be 15 hertz. And you should see CD and BC, and those should be 2 hertz. Okay? So I pulled those numbers right from the diagram on the back of your sheet. That diagram is always given to you. You never ever have to come up with that diagram, those numbers. Yeah? The bar is just a different way to write a J. Yeah, we're so diagrammatic, it's a great question, actually. But yeah, it could be with a bar or without a bar. It's just my 2 ways of writing a J. Okay, all right, I love that question, actually. I'm gonna say that question today at the dinner table. That's gonna be a good question. Okay, here we go. So I'm going to do the splitting tree, and I'm going to track the area like I did here, right? I'm going to track the area in parentheses, the area under the curve, the integration of the curve, as we go through. So HC would start as a singlet, right? And it would be, we'll go with 120 again. I don't know if that's a really good number to start with, but we're going with it. 120. Okay, so I can see that there are 4 protons, right? 1, 2, 3, 4 protons that have non-zero coupling constants. So I'm going to make 4 splits on my tree. Okay? 4 splits on my tree. 1 for every one of these protons. Now, it's easier when you're working on open paper to work largest to smallest. You don't have to do that. If you had graph paper, you can go out of order in any order you want. It wouldn't matter. Okay? But just on an open board, it's easier to go largest to smallest.
On the handout,
Yep.
it says JDB equals JCE and then has 2 values for J of CE. Which is a mistake. But it's still.
I'm like, what did she say?
Sorry.
I have a handout, so I can actually look. Sorry. Okay. So JDE is 10. That's right. JDB equals JCE, which is 2 hertz. But then it says down at the bottom that CD is also 2 hertz. I just didn't put them all together.
Basically, is 15. Your first CE.
Oh.
It should be just BC.
There you go. So third line. Is everyone following along here? Thank you very much. Yeah. The third line where it says JCE, this is right. Okay? JCE should be 15 hertz.
Second line.
The second one should not be CE. See on the far right there, the second line, that needs to be CD. Does everyone see that? Right here.
BC.
Does everyone see this? It should read JDB, which is true. dB is 2 hertz. That's totally right. So that one's fine. And then it says JCE, but that's not supposed to say JCE. It's supposed to say JCD right here. Put this in on the second line. I can fix it and put it online. Let's just put this to bed because we can spend forever trying to fix these things, and everyone's going to be like, what? I can fix this and put it online. These numbers are correct for today. I promise you these are correct. Okay, so if you can work through it on your own, if not, just go collect the new and improved handout that I'll put online.
Yeah.
Now, if we start our splits here, I'm going to start with E because it's 15 hertz. It's the largest one. So I'm going to split 15 hertz. That means the separation here has to be 15, right? It's got to be 15 units in these hertz qualities between them. So I'm going to move 50% of the signal here and 50% of the signal here. So I'm moving 7.5 this way, right, and 7.5 this way. A little bit more. 7.5 this way and 7.5 this way, such that there's 15 hertz in between them. Okay? And the area under the curve now is going to be 60, 60. My peaks don't necessarily, the heights don't represent the integration as much because I need a lot of board space to get down 4 times. Okay, so that's my first split. I'm done. All right, and that's the influence of HE. Now, can everyone see that the influence of HD and both of the HBs are the same? They're all 2 hertz, right? Does everyone see that? They're all 2 hertz. So watch what happens now. As I split here and I go 1 hertz this way and 1 hertz this way, I'm going to be a little bit larger about it just so, you know. If I go with a 2 hertz split, I'm going to get 30-30. And I'm also only going to do one side. I can go back and do the other side in a minute. This is the influence of one of those guys, either HD or HB1 or HB2, it doesn't matter. I'm going to cross out one of them. That's a 2 hertz split. When I do it again for the second one, I get 15-30, because 15 comes this way and 15 comes this way, and this is 15-15, okay? You can't read my tiny little numbers. I split again. I'm now 15 over here. Half the area went this way. These 2 coalesced as they came into their splitting tree. So now 15 meets 15 from this side, and now that's 30. The area is 30. And this guy over here is 15. Okay? And I do it one last time, because that was another HB. One last time is going to go 7.5 over here. I've got to watch my math on these, because sometimes I can really ding it. This would be 22.5 in the middle, right? Because 15 and 7.5, yeah. 22.5 in the middle. Okay? If that math is right, you can tell me in a minute. 22.5, and then finally 7.5. Okay? So this comes down to, again, split 2 hertz in between. So I move 1 hertz one way and 1 hertz that way, and I put lines there. But if I think about what the area is under the curve as I consider that half-half split, I have 7.5 now on the far left, 22.5, 22.5, 7.5. Okay? And this is, as I read it out, 1 to 3 to 3 to 1. Okay? And this is going to come out over here as the same. 1 to 3 to 3 to 1. And this is called a doublet of quartets. A doublet, because they split into a doublet first, and then all of these were the same. 3 of them were the same. 3 plus 1 is 4, a quartet. So it's a doublet of quartets. Okay? Everyone see that? Yeah.
Are we working on the HC or
We're working on HC. Okay? HD is on the back of your handout. HC is the one I just did on the board. So the only ones that haven't been done for you are HE and HB. So what I'm going to do is put those on the weekly quiz, right? So you can practice them, which means there'll be answers for them. I'll give you answers. But I'm going to take questions now. Yes? There's 2 sets of 1 to 3 to 3 to 1. So if we go and look at it, it actually does exist. Everyone flip back to the spectrum side. Does everyone see that signal at 5.1, that's HD, the one we just did? And can everyone see that that really looks like what I'm saying, a doublet of quartets? Do you see on the very bottom, right side, right? The 2 that are to the furthest right there, they look like a doublet of quartets, don't they? They look like exactly what we have drawn up here. Don't tell me that's not cool. That's so cool. You don't get cooler. Yes?
When you split it, does it matter which H?
Does not matter which one you take first. Not at all. Yeah?
So you said the bottom one right here.
Yes.
So this is the doublet of
The
quartet.
doublet of quartets is the set on the far right. So your spectrum looks like this, right? It's a doublet of quartets right here like this. That's D. And then a little bit further, there's a doublet of quartets that's further apart. Oops. So one of them is labeled. So I make a split here. These guys are HD, and these are HE. Okay? So this center is at 5.1 parts per million. Okay? Yeah, in the back, the hat backwards. Yeah. Shh, I gotta hear his question. Go. It's based on neighboring carbons, hydrogens, but, there's a but here, right? Nobody likes the but. The but is that you're so used to looking at just neighboring carbons. Do you see some of this is influenced by things that are 2 carbons away? Yeah. So the idea is that the environment is anything that's close to it. And in these alkene systems, they're smaller, right? Their bonds are smaller. So they still can influence. Isn't that crazy? Yes, there's an influence for something way out here on this proton.
Is that because it's cis or does it not matter?
That is because it's allylic, okay? It's not because it's cis, it's because it's allylic. Any of these sp2's allylic protons, which are right here on this carbon when you're directly next to the alkene, will have an influence, okay? Yeah?
So the second one, the one on the left, is HE or is it HC?
Oh geez, all these numbers, C. Sorry, it's the distereotopic buddy. Yeah.
How do you know that HD is more upfield than HD?
I know from the splits. Now I might not have known that. See, does everyone understand that question? That's such a smart question. How do I know that HC is more upfield than HD, the way that I have it, right? How do I know that, right? And the answer is, I don't know if I necessarily would have known that by the environment alone, taking a scan of the environment. I know that, though, from the splits, because I know that when you look at this splitting tree on the back, right, you're going to find, right, a difference in how it's split, all right? Now, I know this is very, very, like, especially if you haven't seen it before, it's just, whoa. I'm okay with that. I understand that. I'm trying to get you to understand splitting trees. I'll come back in on Monday and do this again, okay? So this isn't the last you've heard of it. If you do have lingering questions, because there's still hands up and I see them, I don't want to ignore you, but I am ignoring you for right now, because we need to move on to the spec packet. So if you still have questions, by all means, we will do this again on Monday, and you're welcome in the office.
I'll send you any
Now,
questions on it. That's okay.
let us talk
I'm gonna do the problems too.
about
Try
the
to
spec
tomorrow.
packet. Does everyone have the packet now? 8 problems. All right, here we go. Today, yeah, if you didn't get one, they're up here. Come grab one. If you didn't get one, it is a stapled packet that has 8 things, or 9, actually there's 9 sheets of paper attached. Come on up and get it. The very last sheet in the spec packet tells you how to integrate, okay? It goes for you through the process of how to decipher how many protons there are for each peak in the NMR spectrum, okay? Practice it. Like I said, you might need this for the lab, and I'm not going to go over it, but I will with anyone who comes into the office. If you don't understand, come in. I will show you if there's any language that's sort of keeping you from being able to do it, okay? So let's just talk about the problems very quick. There are 8 problems. Okay, let's start with problem 1. Everyone see problem 1 on the front has a mass spec, or an IR, that's the top one. Down, right below it is the mass spec. I know that because I see the little M plus with the radical, right? Below that is a C13 NMR spectrum, and below that is a proton NMR spectrum. To the right in the little square under where it says problem 1, that's a UV spectrum. We'll talk about UV spectroscopy actually in the aromatics chapter, so we're going to wait on that. But so that's what that little box is there, okay? You'll see that nowhere on this front sheet is there a formula, okay? And on the front sheet there is also no integration, all right? But if everyone flips the page and looks on the very back of that same page, okay? It's exactly the same spectra with the formula and the integration. So, this is what you can do. If you want, you can practice generating the formula. You can do that through the process I'm going to teach you right now, okay? And you can practice calculating integration. If you want to just be able to solve the spectra, flip it over for every problem, right? Pull out this guy and start from here, all right? So that's totally up to you. So do with it what you may. Today I'm going to go problem 1 through the whole thing, and then we're going to do problem 5. So this is a decision tree. I'm going to speak like I'm a decision tree going through this. I'm going to try and speak out loud how I would go and solve these problems, okay? So, the first thing I can see with problem 1 is I don't have a formula, okay? So, I need a formula, right? In order to do anything, I need a formula. So, how do I get a formula, okay? I start with the mass. The mass is 122. This is the mass of all of the atoms in the molecule, right? So, okay, that's going to help me. Mass is 122. The first thing I'm after is to figure out if there are any heteroatoms in the molecule. Now, the question is, what is a heteroatom, right? That includes oxygen, nitrogen, and the halogens, okay? So I want to know, if there are any oxygens, nitrogens, or halogens. So to get those answers, I'm going to look at the IR, right? I'm going to try and see if the mass is odd or even. It happens to be even, so nitrogen is out, right? And I'm going to try and see if there's any M plus 2 peak, which would, in essence, have a mass peak that would have 2 numbers with a little divider between them, like 88/90, right? 88/90. That would say that I have 2 mass peaks, but I only have 1, right? It only says 122 right there, so that's it. So I have no halogen, I have no nitrogen, but I can see I have an oxygen. How do I know I have an oxygen?
Higher spectrum.
The OH peak up in the IR. Great. Okay, so the first thing I'm going to do is I see an OH, so I'm going to write down alcohol because that's important to me, right? I need to know that there's an alcohol there. That's going to be useful to me. But I know there's a heteroatom, so I'm going to subtract that from the mass, okay? And when I subtract that from the mass, I get now 106, okay? This is saying there's an oxygen present, and I've subtracted it out from the total mass so I can get down to a value for the mass of just carbon and hydrogen alone. So that 106 is hopefully representative of just carbon and hydrogen alone. So my next step is to say how many times does 12, which is the mass of carbon, go into 106, right? So it's going to go in 7, 8, 9 times, right? That'll be 96. And then I would have 10 hydrogens, and then I know the oxygen, okay? Is that right, or is it C8? 8. Off by what? 12 times 8 is 96. We're good. So this is what I get as a formula. Now, the question is, does that make sense? So I'm going to go and think, does that formula make sense? The first thing I'm going to do is figure out how many degrees of unsaturation there are. Now, there's a formula for degrees of unsaturation. I call it IHD. That's the IHD formula. IHD stands for Index of Hydrogen Deficiency, IHD, but really it's just degrees of unsaturation. Okay? So this is going to equal now 1/2, 2 times the number of carbons, minus the number of hydrogens plus halogens, plus the number of nitrogens plus 2. So this is my formula. 2 times the number of carbons minus the number of hydrogens plus halogens. After I've done that, plus the number of nitrogens plus 2. And I take 1/2 of all of that. So if we do the IHD, figuring out how many degrees of unsaturation there are here, I have 2 times the number of carbons, which is 16, minus the number of hydrogens plus halogens, that's 10. So 16 minus 10 is 6, plus the number of nitrogens, that's 0, plus 2, there you go, I have 8. Half of 8 is 4. 4 IHD, right? 4 IHD has very specific meaning to me. It means benzene, okay? Remember, for every IHD, for every degree of unsaturation, you have added a ring or a double bond. That's it, a ring or a double bond. So 4 IHD is specifically benzene. That is, Occam's razor, the easiest solution would be 1 ring and 3 double bonds, which is representative of benzene. Yeah?
Are you supposed to multiply the 6 by 1/2 because you have a 1/2?
No, it's 1/2 of this, because it's outside. You guys are like on me like white on rice. I love it. Okay, keep me honest. You're keeping me so honest. This is good, but I've been docked a few points today. I still want to leave today with an A though, so I'm hoping we might be ending the mistakes. Yeah. That's okay. So I know there's no halogen halogens because, let's just take a for example. If you look, for example, at problem 2. Does everyone see problem 2, the mass specs in the same area, but does everyone see that M plus radical has 2 numbers after it with a sign? There you go. That means that there's an M and an M plus 2 peak. It's a halogen of some kind. The question is that a Br or Cl, right? Okay? But our spectrum that we're working on now doesn't have that, right? It only has one number. So there's no halogen there. Okay? Yeah? Okay, so the 8 carbons came to the fact that when I subtracted out my heteroatom, I got to 106. So that has to be the mass of carbon and hydrogen. So how many times does 12, the mass of carbon, go in there? Goes in 8 times with 10 remainder. See? Yep. Yes?